Are we living in a quantum simulation? The idea that we're all living inside a giant computer simulation has officially broken out of science fiction and into serious, scientific debate. But here's the thing. Almost every popular argument you've heard for the simulation theory gets one fundamental detail wrong. A 2017 study into quantum physics revealed something that doesn't just question the simulation hypothesis. It suggests that simulating our universe is computationally impossible with the physics we currently understand. And the reason why is somehow even stranger than the idea of the simulation itself. Section 1. The seductive idea. Let's be honest, it's one of the most compelling questions you can ask. Is any of this real? Or are we just characters inside some unbelievably advanced computer program, like a cosmic game of The Sims? For decades, this was purely a sci-fi thought experiment, made famous by movies like The Matrix. But recently, the simulation hypothesis has found its way out of theaters and into the conversations of some of the world's sharpest thinkers. When tech billionaires and Oxford philosophers start taking an idea like this seriously, people tend to listen. The most well-known argument comes from philosopher Nick Bostrom. In 2003, he laid out what he called the simulation trilemma, arguing that one of three possibilities has to be true. First, any civilization advanced enough to create a hyper-realistic simulation of its ancestors will almost certainly destroy itself before it gets the chance. Second, a civilization reaches that godlike technological level, but for whatever reason, has absolutely no interest in running these kinds of simulations. Or third, we are almost certainly living inside a computer simulation. His logic is pretty straightforward. If civilizations can build these ancestor simulations, they won't just build one. They'll build thousands, maybe billions of them. And if that's the case, the number of simulated people would dwarf the number of real people in the original reality. So based on pure statistics, the odds that you are one of the simulated minds, rather than one of the original biological ones, are astronomical. That argument is powerful enough on its own. But what really gives it a scientific edge is how bizarre and almost digital our own universe seems at its most fundamental level. Thanks to quantum mechanics, we know that reality isn't smooth and continuous. It's quantized. It's made of discrete, indivisible chunks, kind of like pixels on a screen. There's a smallest possible unit of distance, called the Planck length, and a smallest unit of time. It's almost as if our reality has a maximum resolution. And then you have the observer effect, one of the weirdest discoveries in all of science. It tells us that quantum particles, like electrons, don't really have defined properties until we look at them. Before an observation, a particle is just a fuzzy smear of probabilities. It could be in many places at once. But the instant you measure it, its wave function collapses, and it snaps to one single location. This feels eerily similar to how a video game saves processing power. A game doesn't render every single detail of its entire world all the time. It only renders the environment that the player is actively looking at. So, could the universe be doing the same thing, only rendering reality when a conscious observer takes a peek? It's a spooky and compelling analogy. Even the universal speed limit, the speed of light, seems to fit the theory. On a computer, the processor has a clock speed, a hard limit on how fast it can make calculations. Could the speed of light just be the ultimate processing speed of our cosmic computer? When you put all these clues together, it's easy to see why the simulation hypothesis feels so convincing. It's like the universe is leaving us breadcrumbs. Section 2. The turn. The pivot. So, that's the case for the simulation. It's a strong one. But what if the very thing that seems to support it, the weirdness of quantum mechanics, is actually the thing that tears the whole argument apart? What if all that quantum strangeness isn't a hint that we're in a simulation, but is instead the best evidence we have that we are not? This is where a landmark 2017 study by two physicists, Zohar Ringel and Dmitry Kovarzhin, comes in. They weren't even trying to debunk the simulation hypothesis. Their work was far more technical, focused on the challenges of simulating quantum systems on classical computers. But in doing so, they ran headfirst into a roadblock so fundamental it threatens the entire simulation idea. They were tackling a notoriously hard problem in physics called the quantum sign problem. To put it simply, when you try to simulate quantum systems with lots of interacting particles, the calculations spiral out of control and become impossibly complex. It's not just a case of needing a faster computer. The difficulty doesn't just add up, it multiplies exponentially. For every single particle you add to the simulation, the computing power needed skyrockets. Ringel and Kovrizhin proved that for certain quantum phenomena, this sign problem is basically unsolvable for a classical computer. It's not a temporary hurdle we can clear by just building bigger supercomputers. To give you an idea of the scale, they calculated that just to store the information needed to accurately simulate a system of a few hundred electrons, you would need a memory bank built out of more atoms than exist in the entire known universe. Let that sink in for a second. You can't build a computer inside our universe that is powerful enough to simulate even a tiny piece of that same universe's quantum reality. The program would be infinitely more complex than the machine trying to run it. This just shatters that neat video game analogy. A game only has to render a simplified visual surface. But our universe, even when no one is looking, has to uphold an underlying layer of quantum rules that are so ridiculously complex, they appear to be non-simulatable by any computer we can conceive of. Now the obvious question is, okay, but what if they're using quantum computers? It's a great point. Quantum computers are designed to simulate some quantum systems, but they aren't a magic bullet. They still face massive challenges with this kind of exponential complexity, and it's not clear they could ever handle a simulation on a universal scale. And this brings us to an even bigger problem: energy. Recent studies have tried to calculate the sheer energy cost of running a simulation of our universe. The numbers are just staggering. Simulating our visible universe down to the quantum level would require more energy than is available in the entire universe. Well, what if they just simulated our little corner, just planet Earth? Even that would be a colossal undertaking. The energy required to just run the simulation would be comparable to converting an entire cluster of stars into a single power source. The cost is, for all practical purposes, infinite. This journey from a mind-bending sci-fi idea to a hard physical limit is a perfect example of how science is supposed to work. It takes a wild question and smacks it against the wall of reality to see what sticks. If you think exploring the biggest questions in science is what it's all about, take a second to subscribe and hit the bell so you're here for the next one. Conclusion. So we started with this seductive idea that the pixelated, observer-dependent nature of quantum physics was a sign that we're living in a simulation. It all seems to fit so well at first glance. But when you look closer, the true deep complexity of the quantum world tells the exact opposite story. The quantum sign problem shows a computational wall that seems impossible for any classical computer to ever climb. The sheer amount of information is one thing, but the exponential growth in complexity means that simulating our universe from within is likely a computational impossibility. On top of that, you have the energy bill. Whether you try to simulate the whole cosmos or just our planet, the power needed to run the show seems to exceed all the energy in all the stars. This doesn't mean every possible version of the simulation hypothesis is dead. You could always say the simulators live in a totally different kind of universe, with different laws of physics and limitless resources. But at that point, you're leaving science behind and drifting into pure, untestable speculation. The most popular version of the theory, that beings in a universe like ours could create a simulation of a universe like ours, seems to be ruled out by the very physics it used for evidence. Instead of being proof that our world is fake, the mind-boggling, bottomless complexity of quantum mechanics might be the best evidence we have that our universe is profoundly, fundamentally real. It isn't some simple program running on a cosmic hard drive. It appears to be something far more intricate and mysterious than that. So if we aren't in a simulation, what do all these quantum quirks actually mean for the nature of reality? What does it say about our world that its most basic operations are too complex for even our most powerful theoretical computers to copy? That's still one of the deepest and most exciting questions there is. What's your take? I'd love to hear your thoughts in the comments.